Hello everyone and welcome. In this video we're going to be learning about the world's first variable compression turbocharged engine, which is going to be used in a production vehicle. I'm super happy to say that this video is made in partnership with INFITI, who flew me out to the Detroit Auto Show to see the engine in person and talk with INFITI engineers to learn all the details about how this engine works. And there's a lot of innovation going on. Aside from the obvious of changing compression ratio, we'll also chat about the cylinder liner, balancing characteristics, efficiency characteristics, as well as some of the testing to ensure reliability. So the initial question is, what's a compression ratio and why create a car with a variable compression ratio in the first place? Well, the compression ratio, or the ratio of the maximum cylinder volume to the minimum cylinder volume, can be used to create efficiency and power characteristics of an engine. Now, INFITI wanted to design an engine that could match the power of a naturally aspirated 6-cylinder engine while still achieving the efficiency and torque characteristics of smaller diesel engines, all with improved emissions. So how exactly does it work? Well, the engine operates on the same basic 4 strokes as any other engine: intake, compression, power, and exhaust. That said, it can completely alter the compression ratio to target increased horsepower or increased fuel economy. There are 4 basic steps for changing the compression ratio in this engine. First, a harmonic drive, essentially an electric motor, rotates an actuator arm. Second, the actuator arm rotates a control shaft, similar in principle to a camshaft, which forces a lower linkage to move up or down based on the orientation of the cam lobe. Third, the lower link changes the angle of the multi-link, which is connected by an upper link to the piston. Finally, the upper link moves from the multi-link's rotation, which causes the piston to move up or down, changing the compression ratio. So for example, if the engine was operating in its power mode but wanted to switch to an efficiency mode, the harmonic drive as shown would rotate to the left. This would then rotate the control shaft, which would pull the lower link slightly down. This would rotate the multi-link slightly to the right, which would then force the upper link slightly upward, decreasing the space between the piston and the cylinder head, thus increasing the compression ratio. Okay, so now that we understand how it works, why would you want to switch between compression ratios? Starting with the scenario of creating maximum horsepower, a low compression ratio of just 8:1 is used. This is because the engine is turbocharged. So when you pull in significantly more air and fuel with the turbocharger, you can make significantly more power. However, the likelihood of engine knock increases. Engine knock can be destructive to an engine. However, by using lower compression ratios, you can reduce the likelihood of it occurring. So when the engine is creating its peak power of 268 horsepower or its peak torque of 287 pound-feet, it's doing so by lowering the compression ratio and maximizing boost with the turbocharger. Switching between the two extremes, from a compression ratio of 8:1 to 14:1, or vice versa, can happen in 1.2 seconds. So what about when the engine operates at peak efficiency, at a ratio of 14:1? Well, generally speaking, the higher a compression ratio used, the greater the thermal efficiency of an engine is. In other words, high compression ratios mean better fuel economy. So when the engine is operating at low loads, for example when you're idling or when you're cruising down the highway, it will switch to higher compression ratios to maximize fuel economy. Now, not only does it change the compression ratio, but it also switches from a traditional engine cycle to the Atkinson cycle by altering valve timing. The Atkinson cycle leaves the intake valve open for a short duration of the compression stroke, which means some of the air-fuel mixture is pushed out of the cylinder. What this does is effectively cause the expansion ratio, the piston moving down, to be greater than the compression ratio, the piston moving up, which allows the engine to get the maximum amount of useful work out of combustion. Now, so far I've made it seem like the engine operates in 2 distinct modes, but in reality it's fully variable and can operate at any unique compression ratio between 8:1 and 14:1. Ultimately, the engine will choose the ideal compression ratio for the situation, depending on the driver's throttle input. If the driver is not asking for power, it will adjust the compression ratio to operate as efficiently as possible for the given gas pedal position. And the innovation with this engine doesn't end with a changing compression ratio. There are a lot of unique features. For example, inline 4-cylinder engines are inherently unbalanced. That means that the engines vibrate, and so to compensate, four-cylinder engines often use balancing shafts, which add complexity and consume power, but eliminate the vibration. The reason four-cylinder engines are unbalanced is because of the crankshaft design, which creates a secondary force that is not balanced out based on the movement of the piston. You'll notice, however, that this engine doesn't have balancing shafts, and that's because the geometry of the crankshaft assembly does not cause the piston to create a secondary imbalance. To my knowledge, there's no other inline four-cylinder engine out there that won't have secondary balancing issues without the use of balancing shafts. So not only can it change compression ratio, but it's beautifully smooth and balanced at any compression ratio it chooses. Another unique characteristic of this crankshaft linkage is that it nearly eliminates side forces from the piston on the cylinder walls. In a typical engine, a piston will have a large opposing side force on the cylinder wall as it also pushes downward, rotating the crankshaft. This is because with normal engines, the connecting rod is at a significant angle when rotating the crankshaft. This engine, however, maintains a nearly vertical connecting rod for the combustion stroke as the piston is moving downward, which eliminates the side force from combustion against the cylinder wall. With less force against the cylinder wall, there's less friction, and as the force is all in the desired direction, this is more efficient. Now, looking at the cylinder liner, you'll notice it's very shiny and reflective. This so-called mirror coating is the result of the same plasma sprayed cylinder liner that's used on the Nissan GT-R. After the plasma spray is applied, there's a very fine cylinder bore honing, which ultimately leaves behind a very strong, durable, and highly reflective cylinder liner. The engine also uses both direct injection and port injection. It was found that the most efficient combustion at low loads occurred with both port and direct injection active, and this also helps to keep the valves clean. At higher loads, only direct injection is used, which meets the power demands and allows for precise fuel injection timing. Now, looking at all of the linkages below the piston, it can seem a bit complex, and complexity can lead to reliability concerns. So I asked Infiniti's engineers about their testing protocols, which were used to develop this engine, and what made them confident in the engine's reliability. The testing for this engine, as you might imagine, was quite extensive. The final product is the result of the engine going through over 100 different prototype iterations. From there, the engine has been through over 3 million kilometers of equivalent road testing and 30,000 hours in test beds. Most impressively, 600 development cars were driven around the United States and scattered across the globe, testing the engine in every imaginable climate and weather condition. I asked Infiniti how many cars would be used in testing a more generic engine design, to which they replied about 50. So with 600 test vehicles, nearly 12 times the real-world testing was done on this engine to ensure reliability and durability targets were met. A few other interesting facts about the engine: it has an integrated exhaust manifold, so the distance the exhaust travels to the turbo is extremely short, helping to spool the turbo quickly and also warming up the catalytic converter quickly. The total height of the engine is actually the exact same as other four cylinders, rather than taller from the added linkage. It uses premium octane fuel, and it will be first sold in the Infiniti QX50, though it has also debuted in the Q Inspiration, a concept car highlighting Infiniti's future design language. So a huge thank you to Infiniti for bringing me out to the Detroit Auto Show, giving me an inside look at how this engine works, and of course for sponsoring this video, and thank you all for watching. If you have any questions or comments, please feel free to leave them below.